Hope you can hear me. So I will be talking about material which is not perhaps so interesting technically for most of this community, but it's mostly about applications of several techniques that have been developed by people in the room here on large-scale graph learning. So this is joint work with Daniel Calandriello, Alessandro Lazaric, and Mikhail Valko. By the way, I'm currently at NGIT, which happens to be nearby at Newark. In case you live in the area or you work in the area, you may want to actually talk to me if you want, of course. And this talk is based on a paper that was published last year at ICML, and it's called Improved Large-Scale Graph Learning. Indeed, it is an improvement. I will talk about exactly what it is. So let me start with some introduction and motivation. In machine learning, there's several methods that we can just call graph-based learning. In general, the input will be a weighted graph, or perhaps you can think about it as a matrix. It's a Laplacian. I won't define it. I'm sure you know it. It's a linear operator. And then, in general, we want to compute a labeling, which is a vector f, over the nodes of the graph. And many learning problems and formulations of these problems assume that that optimal labeling that we're seeking to find is smooth, meaning that the quadratic form of the Laplacian f transpose LF is small. Okay. For example, problems or problem formulations that have this assume this general form, Laplacian smoothing with Gaussian noise, which is unsupervised learning, spectral clustering, also unsupervised, harmonic function solutions for semi-supervised learning, and also local transductive regression. So today I will focus on the first two as examples, but what I will be talking about kind of applies on all of them. Okay. So, well, the first example, which is actually a famous problem in theoretical computer science as well, spectral clustering. In its simplest form, we want to compute or minimize actually, this F transpose LF. This is just for one eigenvector. This is for a two-way partitioning. Of course, you can generalize that for k-way partitioning, and this has been a very famous work in the past. Also, example two, Laplacian smoothing, where we have some some vector here f prime, f star, and then we add some random Gaussian noise. There's some variance in the noise with some parameter, and then we want to actually reconstruct that vector here, which can be formalized as minimizing this form here. Now.
Because I could take f equals 0, right?
Okay, so yes, so that
is minimizing over unit sphere to get the smallest eigenvalue or something?
Well, here in this. Oh, well, minimum. Yeah, okay. So I didn't write the constraint. This should be, for example, with unit vector norms, right? So it's the smallest eigenvalue, exactly. Yeah. So. By the way, these are all problems and formulations that were developed probably like 15 or 20 years ago. Okay, so they're pretty old. Well, okay. So how do we solve this? As you said, this is the second eigenvector under this constraint, and the best kind of algorithm, or set of algorithms that we know that we can use to solve this is essentially some version of Krylov space methods or power method. Essentially, this solves a bunch of linear systems of the form Lx equals b, where L is the Laplacian. And in the Laplacian smoothing, if we solve this problem, we get that the solution is this. It's a solution to the linear system L, some regularization parameter lambda times L plus I x equals y. So this is a slightly different system. This is strictly the Laplacian. This one has this regularization parameter, which kind of makes it strongly diagonally dominant. It's a little more in the diagonal than the Laplacian. Okay. Now, as I said, these are all problems. When they were formulated in this way, we didn't have good solvers for the Laplacians, but since then there has been progress, and we know now how to solve these Laplacian linear system solvers and also the diagonally dominant linear systems in time which is, well, I'll just write it as m log m, where m is the number of non-zeros in the matrix or the number of edges in the graph. Well, there's this tilde here that hides a lot of interesting things like the error, some probability of error. Well, but let me state it like this. And the good thing about it from a practical perspective is that there are practically efficient implementations, which are possibly even better than m log m in practice, and maybe even linear time. Okay. Now, the bad thing from a practical perspective is that these solvers require the entire graph to be in the memory. And if we want to have good implementations in the case where we cannot fit the entire graph in the memory, if we want, in other words, to use distributed algorithms, then there are no really good implementations, at least. And yes, Richard.
Among distributed, there has been n to the 0.75 kind of depth, a kind of round algorithm.
So which model?
Congest.
Okay, but okay, so this is a different model. So I'm talking about a simple situation where I have 4 point-to-point machines or something like that. Okay, so this has been by who? By the way, I won't.
It's not published.
It's not published.
Like
Okay.
floating around for like a year and a half.
Oh, okay. So,
Just,
so the congest model is like a different model of distributed computation that we usually have in mind, or people here may have in mind. But anyway, so the point is, let me just speak from a practical perspective. There are no distributed implementations that are in some sense effective with respect to the communication. Everything that we can come up with, or can come up with respect to distributed algorithms requires a lot of communication. So communication is a major issue. Yeah.
Why is this? These solvers require the entire graph to reside in memory.
The ones, the statements,
The first bad bullet.
here.
The graph has to be in memory.
Oh, well,
Why
it's
is
just.
that a problem?
Oh, no. Well, I mean, if the graph is big.
I mean, what's an example of a graph that doesn't fit in memory?
Okay, let me go over that. Okay, so I'll just make this claim. So okay, maybe there's graphs that, I don't know, Facebook or Amazon or this kind of graphs that don't fit in the memory, huh?
The graph of page, right?
Perhaps, some very big graphs. But let's assume, from.
Is there a publicly available graph that doesn't fit in memory?
Okay, so that I agree. Maybe there may be not such a publicly available graph that doesn't fit in memory, but I'm pretty sure that maybe there are, or maybe we could construct. The point is that whatever we construct has this inherent limit, right? So we don't really go over that, perhaps because of that. Okay, so and so I want us to think, I guess, about situations where perhaps not publicly available graphs, maybe on Facebook, they're huge, right? So they have a very big number of nodes, something like 10 to the 1 billion. Some people claim, I'm not sure, that the average degree is 400 or even higher, so the number of edges is near 1 billion. And at that limit, it is the case that maybe we cannot fit the entire graph in the memory. But so let's assume that. So this is going to be a motivation for developing faster algorithms that even can reside in one machine as well, or a small number of machines. But let me just state it as a goal, right? So what if I have a very big graph that doesn't fit in the memory because of the number of edges? The number of nodes is something manageable, but the number of edges is huge. Okay, so now the question here in this setting will be, and that's going to be my motivation, whether we can use some type of distributed resources to do better, theoretically and possibly in practice as well. Okay, so and the answer that this work gives is that yes, we can do something about it. Okay, so now the way I stated it, I said okay, so this number 10 to the 9 is something manageable. The real problem is the number of edges. So what will you do? Okay, let's sparsify. So that will be the first obvious idea here. Let's get rid of edges from the graph. Of course,
you have an average degree of 1 part in a billion there, or 1 part in a million there, right?
Yeah.
You're going to sparsify beyond that.
That's it, right? So that's the thing, right? So we want to actually find algorithms where where that degree is within an interesting range, which you can go lower. Okay, so, of course, if we sparsify, we just start removing edges. For example, uniformly at random, that's not going to be good. It's going to destroy the structure of the graph. So what we will do for the problems that we just discussed is spectral spacification, in particular, read spectral spacification. Okay, so let me just go over the material for spectral spacification. It's standard for most of you. Well, we're going to say that the graph H is an epsilon spacifier of a graph Z if the two quadratic forms are within a 1 plus epsilon minus epsilon factor. Okay, so spectral spacifiers were originally introduced by Spielmann and Teng and used for the design of Laplacian solvers. And today there exist very practical, even single pass algorithms that outputs a sparsifier that has n log n divided by epsilon square edges. Okay, now there are, these constants, this epsilon here and the hidden constant, and this is not clear again, right? So what these exact values are is not clear theoretically, but we're going to make the practical claim that 1,000 or 400 for the average degree is something that you can sparsify in practice and get some improvements. So what is the main idea then? So the main idea is let's get these tools. These are theoretical statements, but let's try to actually apply them in practice and use them as standalone algorithms, sparsification, not for solving, but just before solving for the objective. Okay, and the claim is that current density levels already allow practical computation gains. Okay, so of course, do we do that? I mean, in what cases does spectral sparsification work and why? Well, in theoretical computer science, this was already known. Okay, so I said earlier that in order to solve or find an eigenvector requires solving a lot of linear systems. Obviously, in that case, if we have a very dense graph, we can sparsify it and then hopefully use that for solving our linear systems. And in that sense, we can actually do that and analyze it precisely, understand it, and we can claim that the downstream solution, which is an eigenvector and finally the clustering or the partitioning, does not suffer. So the spectral sparsifier, because it preserves roughly the eigenvalues and eigenvectors, is still going to be good for spectral clustering, and that was understood. Okay? Now, and that happened in 2005. It was already part of the work of Spielmann and Teng. Now, in machine learning, nothing happened in terms of actually using spectral sparsification in a setting until now, 2016, a couple of years ago. Okay? So Sadanala et al. Worked actually with this Laplacian smoothing problem that I mentioned earlier, and they just said, okay, so let's replace this G, the graph that is given as input, with its sparsifier. And when is it worth it doing that? Actually, they have scenarios or settings where a lot of these denoising problems have to be run. And so at some point, it actually makes sense sparsifying so that you solve lots of systems with a sparsifier. So they did that. They actually implemented and ran that, and they observed improvements. And so they also proved theoretical guarantees for the quality of the solution. So I'll come to that later. Now, what is the improvement that the paper we have offers over this previous work? Well, what's the point here? The point is that we have this added diagonal via the regularization that's usual in these algorithms versus the previous case where we just have GNAs. So here we have these regularization terms. And the idea is to exploit this in the following way. So let me go back to what or how some spectral sparsification algorithms work. Well, like the classical algorithm is to actually compute the effective resistances of the edges of the graph and sparsify using those or sampling based on effective resistances. And these are the effective resistances. It involves essentially linear system with a Laplacian. Those are reasonably fast and quite sparse, the sparsifiers that come out of this. and uses linear systems. Now, there's this electrical analogy with effective resistances, and the paper of Sadanala et al. Actually uses a combinatorial method that just approximates these effective resistances and finds the sparsifier. So now, what do we do here? So in order to actually exploit the fact that we have a we have this parameterization regularization parameter there, we're going to define, we're going to define another kind of sparsifier. We will say that a graph H is an epsilon gamma sparsifier of a graph if we have this basic relationship from before, the 1 plus epsilon factor for the quadratic form, but we allow an additive term, an additive error. Okay? So in some sense, the standard spectral sparsifier wants to approximate the entire spectrum correctly. Here we can allow a bit of an error in the lower part of it. Okay, so this has been a main one of the main topics that the community has looked at. So here, of course, it was used or defined for general PSD matrices. Here, we're going to use it in conjunction with the graph structure that our graphs, our matrices have, in order to do some progress. But we're going to concede some bit of an error here. Okay.
If you do that, then turn distinct eigenvalues potentially into multiple eigenvalues, and then the convergence for the eigenvector goes way down.
I'm not sure I'm getting
you know, if you allow that additive term,
yes,
right, plus minus, then it could be that distinct eigenvalues become multiple eigenvalues with that additive term.
Oh.
And then all of a sudden you have a two-dimensional subspace, and the convergence towards an eigenvector goes down.
I agree, right? So this changes completely the objective. It's gonna look different. So there is this difference there. But it's what happens. You know, these are the objectives that people use. So I'm just gonna work with them.
If you have multiple small eigenvalues, why is it better to take one that's bigger than the other?
I'm not saying.
Yeah. So I mean, in that case, it means
I'm just talking about subspace sensitivity. The convergence to a subspace is defined by how far the eigenvalue belonging to that subspace is away from the other eigenvalue. If the eigenvalues are close and you want to converge to an eigenvector associated with that subspace, it's going to be very slow.
But if I have two eigenspaces that are off by machine epsilon, why do I want to converge to one instead of the other?
It's not well defined.
No, I just converge to any linear combination.
No, you certainly want to converge to one instead of another.
I
If they're just doing some
want to cluster a
support.
graph. Right. The only reason that eigenvector is I want to cluster a graph.
Yeah, but you have to make sure your mathematical problem is well defined.
Yeah, just
It is. So you want.
But I mean, the Fila vector is not well defined. If the next
Rayleigh
eigenvalue is
quotients are well defined.
No, the
Well, Rayleigh
sensitivity.
quotients are well defined under this kind of
Rayleigh
equation.
quotient, but not the subspace sensitivity.
But why do I want subspace? I just want
You're
to
computing an
cluster.
eigenvector.
I'm just trying to reduce Rayleigh quotient so I can
And it's
use.
an eigenvector.
No, I just
Well,
want.
It's a linear combination of eigenvectors that you're looking for.
What, I mean, what is your problem? Then
So, you know, when you're going to actually do clustering, what matters is not the precise eigenvector. What matters is the quadratic form of the vector. And so, when you're trying to minimize that, you're trying to get in close to the eigenvector in the sense of the quadratic form of that. So you're allowed to compute a linear combination of very low eigenvectors that are close to that, and that's still okay because it works for your downstream algorithm, your downstream problem. So the problem is the 1 plus epsilon of that quadratic form, not the eigenvector, right? So we're not going for that.
Yeah, from there I can't see that. Okay.
Okay, so it's fine. So
But the only thing you're going to care about is the Rayleigh quotient, or you're going to care about the localization on the eigenvector for downstream?
Well, for the you know, for the clustering, yes, you care about that. So now for the other problem, you know, the smoothing problem, we're going to see. I'm going to give you some error estimates. Okay. Okay. So then what do we do? Okay, so we have sampling by effective resistances. This is Pilman and Srivastava. Now the generalization of that, when we have this gamma effective resistances with the extra additive term, is this, right? So we can actually sample with probabilities proportional to this, which is not an effective resistance anymore, it's some algebraic term, which involves solving linear systems with this matrix.
What do you mean there's no electrical analogy? Adding that gamma
there
I,
is.
like, if you stay off the rank 1 space, that's like adding a Laplacian complete graph. So it ought to be the case that these are effective resistances of a modified graph.
You may be right? So it's not, there may be a graph where you actually add one node and a few edges to the sink or something, and then yes, there may be an analogy of that. But it's not direct as before, okay? Well, okay, so there's no electrical analogy, at least obviously here. And what we're gonna do in order to sparsify is actually solve these linear systems. So what I mean to say is that in the previous algorithm, the previous paper in 2016, they were using a combinatorial solver. They weren't solving, or a combinatorial sparsifier. They weren't solving a linear system. Here, we're gonna be solving linear systems. And what's nice about this is that the required number of samples in this process is actually log n times this effective, distance or effective dimension, let's call it, of the matrix, of the graph, where this is now this sum of the effective of the eigenvalues divided by the eigenvalues plus gamma. And the point here, and that's an important departure from the previous work, this can become less than n. So before, when we do just spectral sparsification in the previous paper, that will be n log n. So we need order n log n. Here we can go lower. And so you can exploit the fact that this gamma is around to go to even sparser graphs. And so that option of sparsifying becomes available to graphs that are not so dense or extremely dense. Yeah.
Log n also to log df?
Can I prove what? Oh, this?
Well,
yeah, most probably yes. But
that was my
most probably this is log d. But d is going to be something big anyway. So if you take the log, it's not going to be extremely small. So it's going to be again log n, right? So roughly. Okay, so that's the thing, right? So we can do sampling, grid sampling here, and go lower in the number of edges. Okay, so we get sparsity gains, and also when you add that diagonal there in that system, when we want to solve this kind of systems, it gets a little easier in practice. So can we state something about bounds, about error bounds? The answer is yes. So even if we do that, like in spectral clustering here, we're going to prove some bounds. So there's two things here. There's the one computed by the exact algorithm without sparsification, and this is computed by the algorithm with sparsification in the paper of Sandanal et al. And they prove that this is actually the norm, the 2 norm, and there's an upper bound. It's related to that, the parameterization the regularization parameter and some other things here. Yeah.
Workshop that has people from several communities.
Yeah, I'm sorry.
Could
Yeah.
you explain what F here is?
Oh, yes. So again, right, so we're trying to do this Laplacian smoothing, and we're trying to approximate that vector F star.
So that's an eigenvector.
So,
Is that an eigenvector?
this is not an eigenvector. So there is an F star vector that we compute, and we were trying to actually find, decode, or denoise, right? So that's the idea.
But it minimizes the quadratic.
And the algorithm, this formulation leads to a linear system, okay? And that linear system, when you solve it, you compute some vector F.
But
Now, I'm not going to characterize how far it is from F star.
yeah, so the F must be an outcome of a mathematical
It
problem.
is the outcome of the linear system. It is the output of the linear system that I just. Let me go back.
So you define your problem by an outcome. Okay.
Well, no, the problem is to actually find that F star. But what people do is to let me go back. So it's going to be.
But this is the second eigenvector in a special case.
No,
In a
it's
special
not.
case,
It's
in a special case, it can be.
Quadratic form. It's a constraint minimization of a quadratic form.
Yeah.
No, this one's from the linear system, I think. Right?
So this is from a linear system. So this is a Laplacian smoothing.
Iteration.
Yeah, he has two.
This is what you define. This is your F star
Yeah, but the lambda
plus some Gaussian noise.
Well, I was looking at example 1. are they the same?
Right? Huh?
I thought you could have solved it.
But it's a minimum,
This is, I
it's
think, a
constrained
constrained
minimum of
eigenvalue.
quadratic form, right?
This one is not. Yeah. Okay. So this is a vector. This can be any vector, any given vector, right?
Oh,
F star.
Generalized.
It's not an eigenvector.
Just trying to understand.
Yeah. Yeah.
Constrained or generalized eigenvalue problem, which in this case is a Laplacian, is also a linear system with the structure.
Right, and the algorithm is via solving a linear system. I could
Yeah,
use
but
the
then
QI
you could
algorithm
have
to
used
do
it,
that.
you could have done it numerically in a worse way if you wanted to.
So-
Okay, so I
Yeah.
understand the problem, thank you.
Okay. So this
It's
is
sort
the
of an
minimization. Then
eigenvector.
you solve the system, right? And then you find a solution to the system. And that solution. Let me go back here. That solution is. Wait. Where is it? This solution is this.
So my previous objection still stands, and never, okay.
Okay, so this is a solution, and F tilde is the solution you get in case you have specified your input, right? So when your graph is specified, you have a specified Laplacian, and so you compute a different solution. So now comparing these two solutions, these two will not be too far. So this characterizes the quality of this, the quality of the specified solution or the specifier-based solution with respect to the one that you compute with the exact solver, without specification. And so it's sum bound, okay?
Does the F hat, is that solved with the regularization, like the
Yeah, there is a regularization parameter here. So this is involved.
But so the exact one, the one that's solved from all of the data, that's without specification, that also uses the same regularization. Right?
Yes, fixed regularization, right? I believe so, right? So I guess this is, this is not what I have worked on here, but I think so, yes. Okay, so now if this paper shows that if H is an epsilon gamma specifier, then you have exactly the previous situation, but you get some additive terms here. Okay, so there's this term and this term as well. So you're going to suffer a little bit in the error, but hopefully, for some range of that parameter gamma that you are allowed to actually pick, that error is not going to be too bad. Okay, so so these two factors, these two terms come again from the gamma, the new problem. And so now, as I mentioned earlier, the problem is to actually be able to do that with very big graphs that have lots of edges. And so the way we should try to do that is try to use some kind of distributed resources. And this is how we're going to do that in general. I'm just going to show a few pictures here. It's going to be based on risk sparsification, and I'll explain what that is. So in the beginning, we're going to have the graph distributed into some number of machines. So I'm going to say distributed, the edges will just be split arbitrarily into a number of different machines. And so there's going to be steps here where the blue ones is when two graphs are just added up, meaning the weights or the edges are collected together. So the size there, when we do that step, is going to be double the number of edges. However, it's still going to be fitting in the memory. We're going to be able to fit that in the memory. And so when we do that, after that, we're going to actually do these the red steps, which is going to be to take that sum and re-sparsify it. And so this re-sparsification will happen by effective resistance. I'm going to have a double the size graph, and I'll just use these ridge effective resistances or gamma effective resistances to sparsify and go down to half the size and make it smaller again. Okay, and you can do that in any kind of schedule, right? So you can start with these two and then combine these two and then combine again at the end. So it's a sequence of merges and the spacification steps. So now, one basic question here is that whenever we have two graphs that are supposedly good sparsifiers and we add them together and then we re-sparsify, then it may be expected, or the obvious thing is that, we're going to accumulate error. Because we re-sparsify, right? So we're going to actually introduce more error. There is an error in sparsification. And so this sequence of re-sparsification steps will actually introduce a lot of error that compounds along the way, and the output will be terrible. So that's the first intuition. And surprisingly, it turns out that if you actually do things in an appropriate way that uses appropriate, I guess, sampling probabilities, the surprising fact is that you can do it without having the error combined or compounded. So, for example, when you merge these two and they have some epsilon quality, they are epsilon sparsifiers, then the resparsification will stay an epsilon sparsifier. Won't go higher in the error.
So why is that?
So the main idea, the way I understand it at least, is that it's because of the fact that this happens independently. There's a lot of independence when you do these sparsification steps. And now there's a formal proof, actually due to Rasmus and Jakub Pankowski and Richard Sussand, which uses matrix martingale. So you can actually prove it using so-called matrix Friedman inequalities. So there's a proof of that. Which is kind of mind-boggling, yes. Not non-intuitive, but it works. And actually, some of the very latest Laplacian linear solvers are based on matrix martingales as well, so by Rasmus. Question?
There's nothing distributed
Yeah.
about this. This is a rule.
No,
for combining
at this point,
at
there's
the
nothing
factor of
distributed,
two
right? So you
levels
can actually
to
do this as a sequence of
preserve that.
steps.
Yeah, yeah.
And essentially, what the paper by this, the previous paper did is to actually do this. I'm sorry, this one, which is a sequential tree. This one is actually a sequential tree. You just start here, and then you do it again, and then you do it again.
I mean, if you did this
Yeah.
in one step, you went in and sampled, you'd lose a lot. I mean, and you said it's surprising you don't introduce error. What would you expect? What sort of a default? Because I would expect that if you did this sequentially, you'd be much better than the sort of one-shot thing. So
When you say one shot, you mean?
You get your effective resistances or the leverage on the edge incidence matrix, and you pull it out in one shot, right? So the reason you do an iterative
Yeah.
method is to get something much finer than that.
The reason you do that, and rather than one shot, is to actually keep it bounded, right? So the size, if that answers the question, maybe not.
So the
So-
total number of points you're using is the same in both cases. You just partition right here.
So you just partition the edges.
So that's why the iterative doesn't necessarily buy you anything because you're using the same amount of samples total, right? It's not like
So the surprising thing is that when you cut back to the same number of samples, it doesn't compound, right?
Right. Okay. So. Okay. So this is a sequential tree. This happens actually as a sequence of merges, but for the case when we have lots of machines and we can actually distribute computation, we can do these things. Like for example, these two nodes can be done independently. 4 machines working here and then 2 machines working here, and at the very end we have one final merge and resparsification, and that produces the sparsifier. Okay, and assuming you have lots of machines, and then you can do it in order log n round. Obviously, you won't have lots of machines, so many machines, but you can exploit your amount of machines to the maximum possible extent by just balancing out this tree. Now, okay, so I think I'm also running out of time. So I have 2 slides here for the algorithm. I'm just going to skip over it. Well, there's a proof again based on martingales that proves that this general arbitrary tree-like sequence works, and I'm not going to go into that. Now, I'll just describe an experiment and see that this can indeed bring some improvements. So we started with a data set which is the Amazon co-purchase graph, which was mined by Young and Leskovitz, which is a natural graph. It's actually a real graph. However, it's artificial in the sense that it is mined. So what happens if for every product you get 4 or 5 different other products that other customers have purchased along the way or with this product? Okay, so you get 4, but presumably there's probably 100 or 200, who knows how many that Amazon knows that are associated with this product. A given product has a conditional or implies a probability that other products will be bought. So in order to actually construct this assumed bigger graph, the more dense graph, that's where the artificiality of it comes in. We're going to actually do, like in Mahoney in a paper in 2015, like random walks in that graph. We just mine that graph, and then we do random walks in that graph, and then we discover merges. So every node, then every product, there's going to be about there's going to be about 300,000 products, and every product is going to have an average degree of 300. So we'll have 300 products connected with every other one on average. So this is a graph where the average degree is on the order or the size speculated to be the average degree on Facebook or even Twitter. Perhaps Twitter is even higher. So now we're going to work with this Laplacian smoothing problem, and we're going to fix our vector f star in this case to be the eigenvector. So we're going to actually select the eigenvector, which is what the previous paper by Sadavana and all did. So we're going to select that vector and then try to see what happens. And so here's a small part of the experimental results. So there's 3 algorithms here. There's the exact algorithm, which is to solve the problem exactly like the original algorithm proposes, which is to solve a linear system using an exact linear solver. Then there's the KN algorithm, which is what? It's the state-of-the-art algorithm proposed in 2016, which is not spectral specification. It's just essentially local uniform sampling with target degree. So you can set K to be, for example, 60, and you can get the degree down to 60. That's again in the paper by Sadanala. And then this is our algorithm, DISRE. Okay? And now you see that the original graph has 98.5 million edges. Then you go down to 15 million edges by this, or with setting the gamma, which is spectral specification, to 22.8 million, and then increasing the gamma, which actually decreases the amount of edges in the output graph, another factor of 2 here, 11.8. So what you can see happening here is there is this error, which is we know this is the reconstruction error now, right? So we know the exact target. It is the eigenvector, and now this is what we compute by the respective method. So this norm here for a sigma is the variance, or we have 2 different variances here. We see that, for example, here we get a very good accuracy, 0.067 in that norm. This goes up to 0.17, which is much higher for this non-principled heuristic, which is a uniform sampling. And then for the random sampling, spectral sparsification-based sampling, it's actually much better. It's close to the exact. And also, increasing gamma is not so important here, right? So despite that additional error term that I had in the expression, we're staying within the same kind of error bounds here. So having this gamma actually works, right? So it gives you much sparser graphs by a factor of 2 without affecting the error so much.
F and V is the exact and approximate eigenvector, right?
V is the exact, which is the hidden vector, hidden by Gaussian noise, and F is the one that you compute by the corresponding method, right?
What is the norm of V?
The norm, which one? This one
Not
here?
the exact factor, yeah.
Of V?
Of V, yeah.
Oh yeah, I mean you can set that to be 1, right? And then
Well, then exact is not doing very well then. You have
I'm
only
not sure exactly what it is the setting in the experiments. I assume it must be 1. But you're saying that
The exact one is not doing very well then. It's getting only 2 digits in the vector.
well, it depends on your definition of well, right? So, but okay, so see, I'm not claiming that the method. So this is a method from 2000, probably 4 or 5, right? And so I'm not claiming that this method is good for reconstructing that. Okay, I'm just saying that here's a method, and let's try to improve it.
But this is also not the error of the eigensolver. Like the eigensolver.
No, this is not the error. This is a different thing. This is a different problem.
This is like the error you get after you compute the exact.
We have Gaussian noise added.
Because they have some noise, yes.
So you're adding.
Solution isn't really the eigenvector.
So this is the smoothing problem. There's 2 different problems, right?
And you generated V yourself, right? It's not.
Wait, no, we actually picked it to be the eigenvector, so we computed it, right? So we computed it to be the eigenvector of that graph, right?
It would be good to see what the noise is, how big the noise is compared to the distance of the next eigenvector. Eigenvalue, that would explain why that happens. Okay, never mind, continue.
But this, what is the theory you laid out say about this? Because there's no spectral gap in this graph. This is an expander.
Yeah.
And so even if you get a relative error on that Rayleigh quotient, so you get a.
There's no
you get
Rayleigh
a-
quotient, he's just having 2 vectors there.
No, but before, even if you got relative error there, this thing's an expander, and now you've added an additive term, and that I don't think says anything about this eigenvector norm difference, does it?
You don't think that there's anything? What? Well, I didn't get it.
The graph's an expander.
Yeah,
Again,
right.
the lambda 2 is a half of
Right.
that graph.
Yeah.
So you say the previous theory says, well, you want to get a relative error for the subspace embedding on the edge incidence matrix.
No,
And
but
you
this
said
is-
add an additive term because the ridge regularization.
No, but this is okay. So the relative error is for, yeah, okay.
That's for the objective of the spectral. It's not about
That's
vectors,
a
it's
spectral method, right? So
Yeah.
this is a spectral clustering,
Yeah.
which is different. Here we have Laplacian smoothing, right? There's
Right.
two different methods.
Right, so what I'm wondering is how does that, if at all, relate to this f tittle minus v norm?
I don't know whether the structure affects things here and in what way, I don't know, right? So we're just doing things in some sense blindly, right? So we're just running this method, which is a simple method, and it's just one of the, there's other more involved
So you're just
results in the
comparing to
paper.
other methods here.
There's more, there's other methods that don't do the same objectives. For example, there is semi-supervised learning, harmonic function, and transductive linear regression. What I'm claiming is that there's this general set of methods that all kind of have the same form. This is a very simple one, okay? But we're trying to see whether this very simple one from a long time ago can be improved, and in what way by spectral, spectral specification. And what I'm stating here is just, we get the older one, we apply it exactly, there is some error, and then that error doesn't go up if we do spectral specification. It's about the same, which means that we can do it, and we can do it much faster. Okay, so we can do kind of the same method, the same objective. I don't know if it's a good or a bad objective. This is an old objective. I don't care so much, but we're just able to do it, compute it within the same kind of error, and much faster. And when I say much faster, I mean what? For example, the exact computation will take 12 minutes. When you have, I think, 4 machines with 32 CPUs each, and then you do this DISRE, our algorithm, plus computing the solution on a specified graph, the entire thing is going to take 3 or 4 minutes, depending on the parameter gamma. Okay, so you can go from 12 minutes down to 4 minutes because you specify it, and you haven't lost so much in terms of the error. Again, this is a very simple objective. I'm not making any claims about the objective. It's not mine. There's 2 more objectives from a long time ago that we also look at the paper, and there's experiments about those as well. And the message is the same, that you can actually specify for like 300, average degree 300 or 500. You can go down by using this approach and get better running times. Okay? And so a few final comments. That's my last slide. So this paper, as I said, was the first paper that actually introduced spectral clustering, spectral sparsification in these machine learning or learning-based algorithms, graph-based learning algorithms. So they're asking whether there's something better. We're asking as well, is there something, some other problems where we can use sparsifiers? That's one question. What we did is to introduce these epsilon gamma sparsifiers. This algorithm, which is a distributed algorithm that constructs this, and also theoretical performance guarantees, not just for Laplacian smoothing, but also LSSL, stable HFS, and LTR. And I'm just going to stop here, and thank you for the attention.
All right, thanks.
Yeah.